Good morning, sir.
So, how are you?
Good morning, sir.
Good morning. I'm just waiting to make participant admit. So, at this moment, I'm still waiting for the participant to get admit. So, in today's class, I will go through the some videos regarding the excretory system. I think almost already I have omitted all the topics regarding the excretory system. So I want to do some videos among you that you can have some idea regarding the excretory system. So, to get started, the very first thing is the basic urinary system. Okay, so let's have this video.
The renal system consists of the kidneys, the connecting arteries and veins, and the urinary tract. The kidneys are paired, bean-shaped organs lying outside the peritoneal cavity in the back of the upper abdomen, one on each side of the vertebral column. The kidneys function as the body's main excretory organ, eliminating the body's metabolic waste products by filtering the blood. Substances that are unneeded or are present in excess are filtered out of the blood and form into urine, moving via the ureter into the bladder before being expelled through the urethra. The kidneys also selectively reabsorb those substances that are needed to maintain the normal composition of the blood. By adjusting blood composition, the kidneys are able to maintain blood volume and pressure, ensure the proper balance of sodium, chloride, potassium, calcium, hydrogen, phosphate, and pH, and eliminate products of metabolism such as urea, uric acid, and creatinine. The medial border of the kidney is indented by a deep fissure called the hilus, where the blood vessels, nerves, and ureters connect to the kidney. The kidney is composed of up to 18 lobes. Each lobe is composed of nephrons. Nephrons are the functional units of the kidney, and each kidney contains more than 1 million nephrons. Each nephron consists of a glomerulus and a system of tubules. The glomerulus is a unique, high-pressure mass of capillaries that filters the blood. The glomerulus is encased in a thin, double-walled capsule called Bowman's capsule. The space inside the capsule and surrounding the glomerulus is called Bowman's space. Plasma-like fluid is filtered from the capillary blood into Bowman's space through the glomerular filtration membrane. glomerular filtration membrane consists of 3 layers of capillary wall: the endothelium, the basement membrane, and the epithelium. This membrane allows some particles from the blood to pass through, but not all. The fluid that is filtered from the capillary blood into the Bowman space is called filtrate and forms the primary urine. The filtrate then diffuses across Bowman's space and into the tubule system of the nephron. In the tubules, some substances are added to the filtrate as part of the urine formation, and some substances are reabsorbed out of the filtrate and back into the blood. The nephron tubule is divided into 4 segments. The filtrate passes through each of these segments before reaching the ureter, a highly coiled segment called the proximal convoluted tubule, which drains Bowman's capsule and where almost complete absorption of nutritionally important substances takes place. A thin looped structure called the loop Bentley, which reabsorbs water and ions from the urine and plays a role in controlling the concentration of urine. A distal coiled portion called the distal convoluted tubule, which regulates potassium, sodium, and pH, and where further dilution of the urine takes place. And the collecting tubule, which joins with several tubules to collect the filtrate and where final sodium regulation takes place. Each kidney is supplied with blood by a single renal artery that arises on its respective side of the aorta, before dividing into 5 segmental arteries that enter the hilum. Within the kidney, each segmental artery branches into several lobular arteries. The lobular arteries further subdivide to form interlobular arteries, which branch off into afferent arterioles. Blood flows into the glomeruli through the afferent arteriole. Blood flows out of the glomerulus through the efferent arteriole. The afferent and efferent arterioles regulate glomerular capillary pressure by selectively dilating or constricting. The kidney's venous blood, now filtered, flows from the glomerulus via the efferent arterioles into the peritubular capillary network, a low-pressure, reabsorptive system surrounding all portions of the tubules. This arrangement permits rapid movement of solutes and water between the fluid in the tubular lumen and the blood in the capillaries. The peritubular capillaries rejoin to form the venous channels by which blood leaves the kidneys and empties into the inferior vena cava. Urine formation involves the filtration of the blood by the glomerulus to form an ultrafiltrate of urine, the tubular reabsorption of electrolytes and nutrients needed to maintain the constancy of the internal environment, and the secretion of waste materials. Filtration occurs as blood flows into the glomerulus from its afferent arteriole, and plasma moves through the glomerular capillaries into Bowman's space. From Bowman's space, the glomerular filtrate moves into the tubular segments of the nephron. Here, through tubular reabsorption, electrolytes and nutrients move from the filtrate back into the bloodstream. Here also, through tubular secretion, substances move from the peritubular capillaries into the urine filtrate. The filtrate concentrates in the collecting tubules, then finds its way to the renal pelvis, where it is directed to the ureter, the bladder, and the urethra for elimination. The kidneys perform an excretory function by filtering the blood and then selectively reabsorbing those materials that are needed to maintain a stable internal environment. The nephron is the functional unit of the kidney and is composed of a glomerulus, which filters the blood, and a tubular component, where necessary substances are reabsorbed into the bloodstream and unneeded materials are secreted into the tubular filtrate for elimination in urine.
Okay. So this was the basic information on how the urinary system, especially the kidney, works. Have you got all? So likewise is, I am going to show another video regarding the function of the nephron. Because nephron is the unit structure of the kidney. So how it works, what it does.
Kidneys are bean-shaped organs which filter blood to regulate levels of waste, water, and salt in body fluids. The nephron is the kidney's functional unit. In its first section, renal corpuscle, filtration occurs as fluid and small molecules in blood are filtered from glomerular capillaries. The filtrate is captured within a chamber called Bowman's capsule. The next nephron section, the renal tubule, has 3 parts in series. Filtrate within Bowman's capsule enters the proximal convoluted tubule. Reabsorption of important molecules and ions from filtrate back into blood occurs here. These include glucose, amino acids, vitamins, water, sodium, chloride, bicarbonate, and potassium. Blood vessels receiving reabsorbed species are peritubular capillaries, a plexus derived from the arteriole leaving the renal corpuscle. The renal tubule continues as the loop of Henle, which has a descending limb passing into the kidney medulla and an ascending limb returning to the kidney cortex. Tubular fluid in the loop undergoes significant changes in osmotic concentration. A countercurrent multiplier system functions to allow water only to leave the filtrate by osmosis during loop descent, and salt only to leave the filtrate by active transport during loop ascent. This creates an osmotic gradient in medulla interstitial fluid. This is necessary to produce concentrated urine. A capillary system, vasa recta, parallels the loop of Henle and participates in salt gradient formation and maintenance. In the distal convoluted tubule, secretion occurs. In some ways, ammonia, uric acid, hydrogen ions, and penicillin are secreted from blood vessels into the renal tubule. If concentrated urine must be produced because of low fluid levels, antidiuretic hormone acts on collecting duct lining cells. Tube section after distal convoluted tubule, promoting water movement from filtrate into interstitial space because of osmotic gradient established and maintained by fluid and solute movement associated with loop of Henle.
So this was the function of the nephron, that how it works. So in these 2 videos, you can see that how our urinary system is working. So being a unit structure of kidney, the nephrons, they are just getting the materials, whatever have to be extracted or have to reabsorb. So regarding this, I have some more videos. Kindly concentrate to this one and make sure that your microphone is on mute. Then only you can have a clear vision.
One of the primary functions of the kidney is better understood at the level of the nephron. In forming urine, the nephron functions to remove metabolic wastes from blood while regulating the volume and composition of body fluids. Urine formation begins in the renal corpuscle, where blood passing through the glomerulus is filtered. Filtrates include water, ions, and other solutes, which are filtered out of the blood and into the capsular space to begin urine formation. Urine passes into the proximal convoluted tubule, then into the nephron loop. The nephron concentrates urine by the process of the countercurrent multiplication system. The countercurrent multiplication system is basically the means by which water and sodium are extracted from the filtrate as it passes through the tubules toward the collecting ducts. This system is called countercurrent because of the dynamics set up by the hairpin turn of the loop of Henle. The direction of flow in the descending limb of the loop is opposite from the direction of flow in the ascending limb. By flowing in opposite directions in such close proximity, a unique interaction occurs. The loop of Henle dips from the cortex of the kidney into the medulla. It is surrounded by the medullary interstitial fluid. The countercurrent multiplication system is responsible for not only elevating the concentration of urine in the loop, but more importantly, it elevates the concentration of the interstitial fluid as well. To explain the countercurrent multiplication system, we must first imagine the loop filled with a stationary column of glomerular fluid, which includes water, salt, and urea. At first, the concentration of the glomerular fluid and the surrounding interstitial fluid will be equal at an osmolarity of 300 milliosmoles. Within the walls of the thick segment of the ascending limb, special pumps extract salt, sodium chloride, from the fluid and transport it to the interstitium. The two areas no longer have an equal osmotic pressure, and a gradient has been established. Within the thick segment, the concentration is at 200 milliosmoles, whereas in the medullary tissue, the concentration is at 400 milliosmoles. Over time, a net diffusion of salt into the descending limb and a net diffusion of water out of the descending limb results in a balance in osmolarity between the descending limb and the surrounding interstitium. Because the thick segment is still actively pumping out salt, the osmolarity of the ascending limb is still 200 milliosmoles, and the interstitium and descending limb are balanced at 400. Salt accumulates in the medulla while water is drawn out of the fluid in the descending limb. Water is removed by the vasa recta, which are capillaries that surround the loops. In real life, operation of this gradient occurs while the fluid is flowing. Fluid flowing in from the proximal tubule and out to the distal tubule, along with the constant pumping of salt into the medulla, contributes to the multiplication of this gradient. As fluid follows the path of the loop, an increasing amount of water is extracted as it reaches the bottom, and an increasing amount of salt is pumped out as the fluid reaches the top. The more salt pumped out, the higher the concentration in the medulla. The higher the concentration in the medulla, the more water is extracted. Eventually, the levels of osmotic pressure are equal horizontally, with the highest value being at the tip of the loop. This level is at 1,400 milliosmoles per liter, which is also the value of the maximal osmolarity of excreted urine. As you can see, fluid becomes more concentrated as it rounds the loop, but it immediately becomes rediluted as it reaches the top. Final concentration of the fluid occurs in the collecting ducts, as it must travel back through the concentrated interstitium of the medulla on its way to the calyces. Urine is concentrated even further in the collecting ducts. The collecting duct must transport urine back through the concentration gradient formed by the nephron loop. The walls of the collecting duct are permeable to water, but not to salt. Therefore, an increasing amount of water is drawn out by osmosis as the fluid travels through the gradient. The gradient provides the force for the concentration of urine, but the rate is determined by the amount of antidiuretic hormone, ADH, in the blood. An increase in ADH in the blood causes the collecting ducts to become more permeable to water. Less urine is secreted and it is more concentrated. A decrease in ADH results in a decrease in water removed. Thus, a larger volume of more dilute urine is excreted.
So in this video, now I think you have a clear vision and idea regarding the urinary system, that how the urine has formed. So there is a diffusion proportion in different parts of the excretory system. So regarding this, as the diffusion occurs in the PCT and also depends upon the rate of the diffusion, the ions and water and other electrolytes, they get diffused from the system to the interstitial cells. So that's how the urine has been formed. So in this thing, one thing is more, that is the vasopressin or ADH. Might you have been seen that the ADH has a very important role for the formation of urine, because when the level of ADH decreases, what happens? The different ions and water, because there is the vasoconstrictor, the volume of the water remains low or less. So the other ions and the concentrates, they have been collected and removed through ureter. So this is the way that how the urine comes. So the next video is regarding the passive transportation in the
Some
excretory system.
proteins in a cell's membrane act as channels for specific ions or molecules. These channel proteins don't use energy at all. They simply allow the materials to naturally diffuse from the side with more solutes to the side with less. Whether the direction is out or in depends on where the concentration is higher for each different solute.
So in this video, you can have a clear
सर
vision.
ये वीडियो में
Pardon?
सर ये काफी फास्ट बोल रहा है, थोड़ा वीडियो को स्लो कर देंगे तो समझ में आएगा.
It is not in my command. It is directly through the YouTube what I have downloaded for you participants or you students. So that's why I am briefing this video that this passive transport video, this suggests that the diffusion of the various ions or the concentrates will be depend completely on the molecular weight and to the rate of ions and the water, or you can say the different concentrations. The next thing is on the male genital urinary system. So before starting this, I think it will be very helpful that you might know about the countercurrent mechanism. I think this has no audio. Anyway, I will just describe it. This is the thing. The various ions, they have passes through the proximal convoluted tubules. You can see the diffusion is there on the basis of the ion concentration. Okay, and from the descending loop, then it go onwards to the ascending limb, and some of the ions are getting in and some are getting out on the basis of their ion concentration and the passive diffusion volume. So this is about the vasa recta. And another way to show the various diffusion system of the ions and concentrations, here you can see very clearly there are so much molecules, sodium chloride, like urea. So how it gets in and how it gets out, and how it gets the interstitial transpiration. Anyway, by seeing you can also confine at how this act, because this regarding the countercurrent mechanism. Next will be on diuretic action. This is a PPT.
As everyone knows, we have two kidneys, each functioning independently.
Let's continue.
Diuretic action occurs in the kidney. This is where the body controls filtration, reabsorption, and excretion of water, small molecules, and ions, such as sodium and potassium. The outer layer of the kidney is called the cortex. The inner layer is the medulla. This is where we have millions of special structures called nephrons. We will now zoom in to a single nephron. The nephron is a tubular structure similar to a porous pipe or hose. The glomerulus serves as the starting point for the flow through the nephron. First, the blood enters the glomerulus through the afferent arteriole. The blood exits the glomerulus through the efferent arteriole. The glomerulus is where the blood supply is filtered by osmosis and diffusion. As blood passes through the porous capillary loops, water and molecules smaller than about 50,000 molecular weight are filtered, passing into the Bowman space. This creates the luminal fluid flowing through the nephron tubule. About 1/5 of the total blood of this volume is reabsorbed, leaving only a small volume to be excreted as urine. Each section of the nephron has a different morphology of cells making up the single-cell wall, which causes differences in water permeability and ion transport. The first section of the nephron is called the proximal convoluted tubule. The proximal convoluted tubule is highly permeable, and about 65% of the filtered sodium and water leak out to be reabsorbed into the nearby capillaries. Old diuretics called carbonic anhydrase inhibitors mostly act on this portion of the nephron. The proximal convoluted tubule leads into the loop of Henle, which has a thin descending limb and a thin and thick ascending limb. The thick ascending limb normally reabsorbs about 25% of the filtered sodium, but does not allow water to reabsorb. The loop diuretics act here by blocking sodium-potassium chloride ion cotransporters on the luminal membrane. The next section is called the distal convoluted tubule. This section does not allow water to reabsorb, but reabsorbs sodium through the sodium chloride ion cotransporters. The thiazide diuretics act here on this transporter. The last section of the nephron is called the collecting tubule. Sodium channel blockers and aldosterone antagonist diuretics act here. At each site along the nephron tubule, certain molecules are able to permeate the wall and leak out into the interstitium. These molecules will be reabsorbed into the paratubular capillary and be returned to the systemic blood supply. Now, we will zoom inside the tubule and then show the molecular details of reabsorption. This is a single layer of cells making up the tubule wall. Ions and water molecules flow through the tubule. This image shows the single-cell layer making up the wall of the ascending limb of the nephron. This sodium reabsorption is driven by the sodium-potassium ATP-PACE transporter on the antiluminal membrane. For every 3 sodium ions moving out of the cell to the interstitium, 2 potassium ions move from the interstitium to the inside of the cell. This causes a deficit of sodium within the cell. This deficit is made up by the sodium-potassium chloride transporter on the luminal membrane of the cell. This transporter moves 1 sodium, 1 potassium, and 2 chloride ions from the lumen into the wall of the nephron. The potassium and chloride ions move down their concentration gradients through their respective channels. The potassium returns to the lumen through a potassium channel. The chloride is removed to the interstitium through a chloride channel. The net result is the continuing transport of 3 sodium ions and 6 chloride ions from the luminal fluid into the interstitium. This sodium is reabsorbed into the circulation. Because of the secretion of potassium, a positive voltage is generated in the lumen, resulting in reabsorption of positively charged ions through the paracellular junction. When the sodium-potassium chloride transporter is blocked by the loop diuretics, the sodium-potassium exchange begins. But the sodium deficit cannot be replaced by the sodium from the lumen. This blocks the overall reabsorption of sodium from this site in the nephron. The net result is greater excretion of sodium, chloride, potassium, calcium, and magnesium in the presence of the loop diuretics. The next site for diuretic action is the distal convoluted tubule. This is where the thiazide diuretics act. The transporters present in the distal convoluted tubule are slightly different than those described in the ascending limb. In the distal convoluted tubule, the sodium chloride cotransporter replaces the sodium deficit caused by the sodium-potassium ATPase. The chloride is reabsorbed through chloride channels, and the potassium returns to the interstitium through a potassium channel. The sequence results in overall sodium and chloride reabsorption. However, the thiazide diuretics bind at the chloride binding site and block the sodium chloride cotransporter. This blocks sodium and chloride reabsorption, resulting in net excretion of sodium and chloride. The last site for diuretic action is the connecting and collecting tubules. This is where the sodium channel inhibitors act. Again, the transporters present in the collecting tubule are slightly different than at the other sites of the nephron. At this site, the same sodium-potassium exchange occurs on the antiluminal membrane. However, the sodium is replaced at this site through the sodium channels on the luminal membrane, and potassium excretion is completed by transport through potassium channels on the luminal membrane. This continuing exchange results in overall sodium reabsorption and potassium excretion. When the sodium channel inhibitors are present, they block the sodium channel. This prevents the continual reabsorption of sodium and also prevents the overall excretion of potassium. This is why sodium channel inhibitors are called potassium sparing. Thus, all of the diuretic agents described directly decrease the reabsorption of sodium by blocking specific ion transporters in the various segments of the nephron tubule. This indirectly affects reabsorption and excretion of water and other ions, as described for each type of diuretic.
Okay, so this is the almost the overall schematic and videographic picture regarding how the kidney works. What will be the different concentration gradient and how different ions, water, they get diffused. So I think this class is most better to understand how our excretory system works. So regarding this thing, I have so many videos, but just I want to show one or more small video. I think it will be very helpful for you. No? This one, no? This is a This is about the nephrectomy. I don't know the time will be so much regarding this or not, but hope for so.
Line just above the umbilicus. The working ports and camera ports are placed lateral to the hand incision.
This is about the nephrectomy. This is totally regarding the surgery, but just to know where it is situated and how it works.
The lap disc is placed and the abdomen is insufflated. The stomach is decompressed with an orogastric tube. Prior to placement of the working port, the bowel is retracted medially and the kidney is palpated during a visual inspection to ascertain its precise location. The colon is reflected medially and mobilized superficially as the harmonic scalpel laparoscopic curved shears, the LCSC5, are used to incise to the white line of Tolt. The visualization is excellent as dissection continues medially up to the medial aspect of the kidney to ensure adequate mobilization of the colon during the hilar dissection later in the case. Care is taken to avoid sizable blood vessels in the fatty tissue near the pancreas and stomach. Dissection continues. The renal artery is exposed. 1 or 2 clips can be placed on the artery in order to flatten the renal vein, facilitating its division. Here, the renal vein is visualized, but an inadequate length of the artery is controlled. Since the vein is flattened nicely, dividing it offers additional access to the renal artery. The vascular stapler is passed, as a digit helps guide the...
So this is about the things, how it works. Basically, almost the time is over. So if you have any query, you can have any question on the group WhatsApp, or maybe for the next class. One scheduled class I will be make for discussion on excretory system only, because after 2 days you have got the class schedule. The home is going to be take the class on which day. So I think Friday will be the right